Welcome to Lab 11 on thick lenses. We'll quickly review the theory of thick lenses, especially those built by two thin lenses, and then get into the lab details. As you've seen from the notes, two thin lenses can be treated as a thick lens, and thick lenses have two principal planes, H1 and H2, two nodal points, N1 and N2, and two focal points, F1 and F2. The way that we can complete ray tracing depends on the location of the principal planes and the focal points. These points serve as the location where rays will make their bend in a ray diagram. So if we place an object upstream, we can trace the parallel incoming ray to H1 and then the exiting ray through F2 from H2. You'll notice it looks like the ray sort of fast forwards from H1 to H2. The incoming ray from F1 leaves parallel from H2, and the incoming nodal ray hits N1 and then leaves parallel to its incident angle through N2. We can cast these together to form the image location. Locating these nodal points is a main focus of the lab. For this setup, this will be the thick lens that we're using. It's constructed of a PVC pipe with one lens at this end and another thin lens at this end, so that effectively will act like a thick lens. I've started off by auto-collimating a 5 diopter lens, so this distance is roughly 20 centimeters, and we have parallel rays leaving that lens, entering our thick lens. And the first thing I do is locate a clear image on the screen, and that tells me the location of the secondary focal point. Again, parallel light coming into this thick lens comes to focus at this distance. Next, I'm going to use the Nodal Slide and the fact that I can pivot this lens to find the nodal points and the principal plane. If I rotate this around a nodal point, the image will stay stationary. So clearly this is not currently rotating around a nodal point. So I'll move the lens in the slide by loosening it and sliding it a little bit this direction and try again. You can see there's less motion. If I go a little bit farther, see reduced motion further. So I can continue moving this nodal slide until I find the location where there's no relative side-to-side motion. You'll notice that I have to refocus this image after a little bit because I'm no longer at the secondary focal point. Clear image there. Check for motion. It's fairly stationary. You can see I'm moving this quite a bit and there's not a lot of motion. So I'm going to fine tune. I want to go till that motion reverses, and then I know I've gone too far. And you can see the motion is going up in the opposite direction. So somewhere here is where this motion is actually 0. So I'll look in close. I'd say that's pretty good. I found the exact nodal location. You can see by moving this lens quite dramatically side to side, I see no motion of that image. That means the nodal point is immediately above this pivot point here. So I can measure above that crossed circle right here to the back vertex of the lens. Now you see I've flipped the lens and the light source to the other direction, so I'm sending light backward through the thin lens, through the thick lens. I'm sending light backward through the thick lens. You'll see this says the front. This is the front of the lens. I'm sending light backwards. This is how I can send parallel light backwards through the lens and measure the primary focal point. So you see I found a clear image here. Get that nice and focused. That would be the primary focal point, F1. So I can measure this distance from the front of the lens and locate F1. Now I can repeat the nodal slide approach, pivoting and finding a clear, a stationary image in this direction. So again, sending light backwards through the lens. So this will be locating the primary nodal point and primary principal plane. So if I start here, I see that there's some motion of the image, reduced motion, now opposite motion. Again, too far, I see with motion. And then here I see against motion, so in between is going to be just right. So I keep fine-tuning forward or backward until I see no relative motion there. And that looks pretty good right there. Yeah, so I'll tighten this down and show everybody where this one is. So I see, again, no motion in that image. And now I can measure this, and again, this is now from the back vertex. I can measure from the back vertex to the pivot point here. This diagram is not to scale, but it does indicate the 4 measurements that we collected in the lab. Additional information you'll need is that the full length of the lens is 7 centimeters, and the powers and spacing of the lenses are listed shortly. For part 6, I've placed an object 40 centimeters upstream from the front of this thick lens, and then we can locate a clear image. Turns out this image forms 48.5 centimeters downstream from the back vertex of the thick lens. And again, just for reference, the full length of this lens is exactly 7 centimeters. For your calculations, you'll need these additional measurements. The power of the front thin lens is -2 diopters. The power of the back thin lens is +5.5 diopters. And the distance between them is 61 millimeters.